Hello, one and all, and welcome to my poster. The topic of the research that I'm presenting today is about testing the sensitivity of clot radiomic features computed from CT imaging of patients with acute ischemic stroke and testing the sensitivity of these features to inter-user segmentation differences. So starting from the top, radiomics is an emerging field that is currently a promising tool for analyzing variations in textures or patterns of signal intensities from medical imaging, and more specifically in the field of acute ischemic stroke intervention and management. There have been models that use subsets of these radiomic features that help predict the outcome of the standard of care, which is mechanical thrombectomy, even before the procedure is done, so as to have an idea of whether or not a procedure is going to fail, so as to better be able to manage the patient and have a better outcome. As I said, there have been multivariate models that have shown high accuracy in prediction of outcomes before the actual intervention using subsets of these radiomic features that are computed from pre-treatment CT imaging. However, none of these studies have tested the sensitivity of the key radiomic parameters in determination of these RFs and the effect of interior segmentation repeatability, which remains an unexplored area, but is definitely an important consideration for standardization of radiomics-based image biomarkers. To test this in our study, what we did here is we collected the CT imaging before acute ischemic stroke patients underwent mechanical thrombectomy from 17 patients. For these 17 cases, what we did with these cases is did manual segmentation, and to explain to the audience how that is typically done, I would like to draw your attention to figure 1 on the bottom left right here. Typically, this clot that causes the ischemic stroke it typically lights up as a hyperdense region, as you can see by the arrow that points to this hyperdense, like tiny hyperdense region that you see on the NCCT or the non-contrast CT imaging right here. And at the same location on the CTA or the CT angiography in figure 1B, you see a lack of contrast, which basically means there is something solid there that is not allowing the contrast to reach there, essentially meaning that there is a clot there. So while following both these co-registered images, you identify or delineate, like going through slices, a 3D clot. And from these 3D clots, you have this open source tool called PyRadiomics that allows you to calculate, in our case, 200 features from both a total of 200 features from the non-contrast CT and the CTA imaging. And for these radiomic features are typically categorized into 3 major categories. First is 3D and 2D shapes. Second is first order statistics of intensities within the region. And the third category is the texture, or the way lower and higher intensities show patterns of repetition or non-repetition within these regions from the NCCT and CTA images, which are typically computed from these 5 texture matrices. So those are the 3 categories of features we computed from NCCT and CTA imaging, and we varied what is called bin width, or the discretization of images based on intensity ranges. We tested out 2, 4, 8, and 16 to test out whether or not these features are sensitive to the widths of the bin discretization. So firstly, for the NCCT features, what we clearly observed was shape features were doing amazing. The first order features and the texture features were doing pretty well in terms of ICC. And what we saw consistently for NCCT and CTA images was, if you go from a smaller bin width to a higher bin width, the performance or the ICC reduces. Again, what ICC here is for a given value of bin width, what was the feature computed as across 3 users based on the segmentation that the users did. So a higher ICC basically indicates a better reliability across users in computing a specific type of feature. So going from left to right, you see an increase in the value of bin width, but a decrease in the average value of interclass correlation coefficient, basically showing that with increasing bin width, you saw a decreasing reliability of radiomic feature computation. Similarly, what we saw in CTA images was also a very similar trend where you see going from left to right, the value of ICC decreases. What we saw was these ICCs typically ranged from 0.39 to 0.82, clearly indicating that before any radiomic feature subset thrown into a multivariate model for predicting the outcome, you should clearly do this analysis to identify features that are highly sensitive to segmentation and basically just remove those features, or the features that are not reliable enough. If you're using a manual segmentation technique, the features that are not reliable should basically be removed in the analysis. What we also saw in general was, as you can see from the ICC values on both CTA and the NCCT, the ICC values on the NCCT are clearly higher as compared to ICC values that you see on CTA, which basically indicates the radiomic features computed from non-contrast CT images were probably more reliable than radiomic features computed from CTA plot regions. Again, as I said, average ICCs observed across all features was higher with lower bin widths for both the NCCT and CTA radiomic features. And optimal bin widths for radiomic feature computation from both the CTA and NCCT, as I mentioned, was found to be 2. So the lowest bin width was something that was giving the best performance. Now, from this point forward, we just stuck to the best bin, the bin width that gave us the best ICC, and which was a bin width of 2. And using that, we tried to count how many of these features yielded a good and a moderate agreeability, which basically means good meaning ICC greater than 0.75 and moderate meaning ICC greater than 0.5. And we saw that a total of 100 and 150 gave good and moderate agreeability respectively. Again, based on the ICC values of optimal bandwidth of 2, we saw that a total of 25 NCCT and 6 CTA radiomic features respectively achieved an excellent reliability score as well, which can also be seen in the figure 4 right here. You can again consistently see that for the features that showed excellent reliability, clearly the NCCT features are doing a much better job compared to the CTA features, because the red line you can see is clearly further away from center compared to the blue line right here. Again, these dots are ICCs corresponding to the feature name that you see concentrically written outside the circle. So based on all these observations, we were able to conclude that these radiomic features are clearly sensitive to these bin widths, to how the user segments these plots. We also were able to see that probably before introducing these radiomic features to multivariate models, it might be necessary to basically do a filtering based model, a filtering based feature reduction step, wherein you basically just get rid of features that are not reliable enough. And in our study, we also saw that ICC for features from NCCT was clearly higher than features from CTA, basically telling us that radiomic features from NCCT are more reliable than features coming from CTA images. With that, I would like to thank the funding resources, which was from National Institute of Health, and also RPI, Dr. Vincent Totino, for all the help with this work. Thank you so much.